Welcome to this lecture on the limiting form of the t-distribution. Imagine you are trying to find the average height of students in a massive university. If you only measure 3 students, your calculated average will be highly unreliable and the spread of your possible errors will be very wide. But as you measure thousands of students, your estimate becomes incredibly precise. Today, we will explore the mathematical bridge between small sample uncertainty and large sample predictability and see exactly how the t-distribution transforms as our sample size grows. Now that we understand the basic premise, let us look at the core concept. In statistics, when we have a small sample size, the spread of our data is perfectly described by the student's t-distribution. This distribution has what we call heavy tails, meaning extreme values or outliers are much more likely to occur than in a normal bell curve. The shape of this curve depends entirely on the degrees of freedom, denoted by the Greek letter nu, which simply refers to the number of independent data points available. As nu increases, meaning we gather more data, these heavy tails shrink. The peak of the curve gets taller and narrower. Ultimately, as the degrees of freedom approaches infinity, the complex t-distribution simplifies completely and converges into the standard normal distribution that you already know. This concept leads us to the mathematical equation that draws the shape of the probability curve. This is the probability density function, or PDF, of the t-distribution. It looks intimidating, but we can break it down. The function f of t gives us the height of the curve at any given point, t. The symbol nu represents our degrees of freedom. The capital Greek letter gamma represents the gamma function, which is an advanced mathematical tool that extends the concept of factorials to continuous numbers. The equation has two main parts, a complex constant fraction at the front involving these gamma functions and a variable part at the end involving t and nu. If nu increases, the fraction at the front stabilizes, and the exponent at the back drives the shape of the curve toward a normal bell shape. Now that we have seen the formula, let us prove mathematically that it turns into the normal distribution. We must take the limit of the PDF as the degrees of freedom, nu, goes to infinity. To do this, we will first focus on the variable part of the equation at the end. We start by splitting the complex exponent into two separate pieces using basic algebra rules. We separate the negative nu over 2 power from the negative 1/2 power. This allows us to evaluate the limits of these two pieces independently. By breaking the problem down this way, we can apply standard calculus rules to see exactly how the variable t behaves as our sample size grows infinitely large. Continuing with our derivation, let us evaluate these two limits. The second piece is raised to the power of negative 1/2. As nu grows infinitely large, the fraction t squared over nu approaches 0. 1 plus 0 is 1, and 1 raised to any power is simply 1. So that entire piece vanishes. The first piece is where the magic happens. We use a famous calculus rule which states that the limit of 1 plus x over n, all raised to the power of n, approaches e to the power of x. Applying this rule, our term transforms directly into an exponential function involving e, Euler's number. The result is e raised to the power of negative t squared over 2. Finally, we bring everything together to get our final result. We just found that the variable part becomes e to the power of negative t squared over 2, which is the exact core shape of the standard normal bell curve. Meanwhile, using an advanced mathematical tool called Stirling's approximation, it can be shown that the complex constant fraction involving the gamma functions perfectly simplifies to 1 over the square root of 2 pi as nu approaches infinity. When we combine this simplified constant with our simplified variable part, we get the exact probability density function of the standard normal distribution. We have successfully proven that for very large samples, the t-distribution mathematically transforms into the standard normal curve. So we have proven that this convergence holds. This brings us to an important practical question. How quickly does this happen? For very small values of nu, the t-distribution is critically larger in the tails than the normal curve. The most extreme case happens when nu equals 1, known as the Cauchy distribution. Its tails are so incredibly thick that its mathematical mean does not even exist. If you try to calculate an average, the numbers swing wildly forever. When nu equals 2, the mean finally exists, but the variance is infinite. However, as nu grows, the tails shrink rapidly. By the time nu reaches 30, the t-distribution is so visually and mathematically close to the standard normal curve that statisticians simply use the normal table as a practical shortcut. To truly understand this, let us look at a visual representation. In this graph, the horizontal axis represents the t-value, and the vertical axis represents the probability density. Look at the red dotted line at the bottom. This is the Cauchy distribution, where nu equals 1. Notice how flat it is and how thick the tails are on the far left and right. Now look at the blue dashed line, where nu equals 5. The curve has pulled inward from the tails and pushed upward at the peak. Finally, the solid black line is the standard normal distribution. As the degrees of freedom approach infinity, the curve locks perfectly into this solid black line. The heavy, unpredictable tails vanish completely. Now that we have seen the visual convergence, let us look at how the variance behaves mathematically. The variance of a t-distribution is given by a very simple formula. V equals nu divided by nu minus 2. Here V represents the variance, which measures the spread of the data. The symbol nu represents the degrees of freedom. Note that this formula only works for nu strictly greater than 2, because as we learnt earlier, the variance is infinite when nu is 2 or less. As nu increases, the numerator and denominator get closer in value. Since the standard normal distribution has a known variance of exactly 1, we should expect this formula to approach 1 as our sample size grows. Before we move on, let us see this with a concrete example. We will calculate the variance for different degrees of freedom to observe how it approaches the standard normal variance. First, let us plug in a small sample size with nu equal to 5. We substitute 5 into our variance formula, giving us 5 divided by 5 minus 2. Performing the simple subtraction in the denominator leaves us with 5/3. This step shows us exactly how much wider the spread is when we only have a few independent data points to work with. Continuing our calculation, 5 divided by 3 is approximately 1.667. This is significantly larger than the standard normal variance of 1, proving that the curve is much wider for small samples. Next, we test nu equal to 30. This represents a much larger sample size, which is our practical threshold for normal convergence. We substitute 30 into the formula, giving us 30 divided by 28. We are already seeing that the numerator and denominator are becoming very close in value. Let us find the final answer for this example. 30 divided by 28 drops the variance to approximately 1.071. This is extremely close to 1, which proves our practical rule that at 30 degrees of freedom, the t-distribution is nearly identical to the normal distribution. Finally, if we take the limit as nu approaches infinity, the minus 2 in the denominator becomes completely insignificant. Nu divided by nu is exactly 1. As the degrees of freedom grows infinitely large, the variance becomes exactly 1. This perfectly matches the variance of the standard normal distribution, confirming our theoretical derivation with concrete numbers. Now that we have used this formula, let us understand how this helps us in the real world. When researchers analyze massive data sets with hundreds or thousands of degrees of freedom, looking up exact values in a massive t-distribution table is completely unnecessary. Because the t variable converges to the standard normal variable, denoted by z, we can simply swap them out. This limiting form property allows us to solve complex probability problems for massive sample sizes easily using the basic standard normal tables we already have. We do not need specialized software or enormous statistical tables to get highly accurate results. Let us apply this practical shortcut to a real problem. A researcher has a massive data set with 1000 degrees of freedom. They need to find the probability that the t-statistic is greater than 1.96. Because 1000 is vastly greater than our practical threshold of 30, we replace the complex t variable with the simple standard normal z variable. So we just need to find the probability that z is greater than 1.96. Standard tables only show less than probabilities, so we take the total probability, which is always exactly 1, and subtract the probability of being less than or equal to 1.96. Now for the final steps. We look up 1.96 in a standard normal table, which tells us that the area to the left is 0.9750. We substitute this value into our equation, giving us 1 minus 0.9750. The final probability is 0.025 or 2.5%. By using the limiting form of the t-distribution, we easily solved a complex probability problem for a massive sample size. The physical meaning here is that there is exactly a 2.5% chance of observing a value this extreme in such a large data set. We have covered a lot of ground today, so let us review the key takeaways. The limiting form of the t-distribution is a beautiful mathematical bridge. It shows us exactly how small sample uncertainty transforms into large sample predictability. We proved mathematically that as we gather more data and our degrees of freedom approach infinity, the heavy, unpredictable tails of the t-distribution vanish completely. It locks into the perfect symmetry of the standard normal curve. Understanding this convergence is crucial because it justifies why statisticians can safely use simpler normal distribution formulas whenever their sample size exceeds 30. You now have a solid understanding of this fundamental statistical concept.